Welcome to this explainer. Today, we're diving into one of the absolute most foundational and honestly kinda dense topics in mechanical engineering, the milling machine. I want you to picture this explainer like we're exploring a fully interactive 3D CAD model together. We're going to start from the absolute outside, looking at the massive macro structure of these heavy-duty machines, and then slowly zoom in. We'll go right past the steel casings down to the literal microscopic point where the cutting tool physically shears through solid metal. So let's just get right into it.
Just to ground ourselves quickly, here is the fundamental definition. Milling is a machining process using a rotating, multi-point cutter to remove material from a workpiece. Now, you know how on a lathe the workpiece spins and the tool stays stationary? Well, milling completely flips that dynamic. Here, the workpiece is clamped firmly in place, and a multi-tooth cutter spins at crazy high speeds, plunging into the metal to carve out incredibly complex, precise parts from a solid block.
Okay, here's our roadmap. 1. Machine anatomy and construction. 2. Kinematics and gearbox equations. 3. Up milling versus down milling. 4. Operations and tool geometry. And 5. Parameters, indexing, and applications.
Section 1. Machine anatomy and construction.
Think of this next part like an exploded assembly diagram. It all starts at the bottom with the heavy cast iron base and the super rigid vertical column that literally supports the entire shebang. Now, riding up and down on the face of that column is the knee. That gives us our vertical motion. Sitting right on top of the knee is the saddle for your in and out cross motion. And finally, the table, which holds the workpiece and moves longitudinally, left and right. Above all of this sits the spindle, the spinning heart of the machine, which usually uses an arbor and an overarm to rigidly hold the cutting tools in place.
Now, while that basic anatomy applies across the board, milling machines do come in a few distinct flavors. Horizontal machines have a spindle parallel to the table, awesome for heavy material removal. Vertical machines have a spindle perpendicular to the table, which is ideal for plunge cuts and precise facework. Universal machines add this cool swivel feature to the table for complex angles. And of course, there are CNC milling machines. But you know what's really fascinating? Even though a modern 5-axis CNC looks like a sci-fi spaceship from the outside, underneath all those digital interfaces and sleek covers, it's still relying on that exact same foundational base column spindle anatomy as a 100-year-old manual mill.
Section 2. Kinematics and gearbox equations.
If we peek under the hood at a kinematic diagram of a milling machine, we're basically tracing the physical transmission path of power. It starts at step 1 with the main motor drive. That rotational energy gets fed directly into the speed gearbox, which is this really complex array of shafts and gears that steps the RPM up or down before delivering it to step 3, the spindle. But here's the kicker. Power doesn't just go to the cutter. It's actually split. Through another set of transmission paths, power is diverted down to step 4, the feed gearbox. This is the incredible mechanism controlling the automated longitudinal, cross, and vertical motions of that heavy table we just talked about.
Driving all of that mechanical motion is a very strict set of mathematics. The spindle speed equation, denoted as N, is essentially the mathematical heartbeat of the machine. You see, engineers don't just guess how fast the spindle should spin. No way. They calculate it precisely based on the desired cutting velocity for the specific material being machined, plus the diameter of the cutter. Getting this equation right is absolutely crucial. Run it too fast and you're going to burn out the tool instantly. Run it too slow, and you risk tearing the machine apart through excessive friction. It's a delicate balance.
And then you have to connect that spindle math to the feed rate equation. The feed rate is simply how fast the table pushes the solid metal into the spinning cutter, and it's intrinsically linked to the cutter's rotation. You calculate it by taking the desired feed per tooth, which is literally how big of a chunk of steel each blade rips out per revolution, multiplying that by the number of teeth on the cutter, and then multiplying all of that by the spindle speed we just calculated. This ensures the physical movement of the table perfectly matches the rotational physics of the tool. It's a beautiful system.
Section 3. Up milling versus down milling. Zooming in on the actual cutting action, there are 2 fundamental ways to feed metal into a cutter. In up milling, which is also called conventional milling, the chip thickness starts at essentially 0 and kind of rubs its way up to a maximum thickness. Because of this, the cutting force actually tries to lift the workpiece right off the table. But in down milling, or climb milling, it is the exact opposite. The cutter bites into the maximum amount of material right away, and the chip tapers down to 0. And most importantly, the cutting force pushes the workpiece safely and securely down into the table.
The reason for these massive differences all comes down to opposing rotational forces. In up milling, the cutter rotates against the direction the table is feeding. They're literally fighting each other. In down milling, the cutter rotates with the direction of the feed, almost like it's trying to climb over the metal. Choosing between climb and conventional milling completely dictates the stability of the entire cutting process, the surface finish you get, and exactly how securely you need to clamp your parts. Because let me tell you, if you get it wrong, especially in climb milling, the machine will literally throw the heavy metal across the room, for real.
Section 4. Operations and Tool Geometry.
Because a milling machine is so wildly versatile, it can perform dozens of distinct operations. Instead of doing it all one way, you can use face milling for perfectly flat top surfaces, or maybe switch to peripheral and slab milling to flatten wide expanses from a horizontal setup. End milling is absolutely your go-to for pockets and crisp edges. Then you've got slot milling to cut deep channels, gang milling to machine multiple surfaces all at once, and form milling to carve totally custom complex contours. Each unique setup carves a distinctly different 3D profile right into the workpiece.
Now, to pull off those operations, you obviously need the right tool. An end mill looks a bit like a drill bit, but it cuts on its sides as well as its tip. A slab cutter is this wide, cylindrical tool used mainly on horizontal machines. A face mill is a large, disc-like tool with these removable cutting inserts around its edge, specifically for flattening large blocks of steel. And speaking of those inserts, they're often coated in super high-tech materials like titanium nitride, so they can survive thousands of degrees of heat without melting. Finally, you have a slitting saw, which is exactly what it sounds like, a thin, circular blade for cutting deep, narrow slots or just parting off material entirely.
But these tools aren't just sharp, they are precisely engineered wedges. If you look really closely at the tool geometry, the rake angle dictates how aggressively the tool shears the metal and directs the chip flow. The clearance angle ensures that the back of the cutting tooth doesn't just drag and rub against the freshly cut surface. And the helix angle, which is that twist of the flutes, helps evacuate chips smoothly and severely reduces the shock of the teeth slamming into the metal. These precise angles are what ensure the tool actually slices efficiently rather than just mashing against the steel.
Section 5. Parameters, Indexing, and Applications.
Ask any machinist, and they will tell you that success always comes down to balancing three primary parameters: cutting speed, feed rate, and depth of cut. We've already talked about the math behind speed and feed, but you also have to heavily factor in how deep you're plunging that tool. If you get all these formulas right, you get this beautiful mirror-like surface finish, and your ridiculously expensive cutting tools will last for hours. But if you get them wrong, you'll shatter the tool, ruin the part, and potentially do serious damage to the machine itself.
Now there's one specific accessory I just have to mention: the indexing head mechanism. This thing is an absolutely brilliant kinematic trick. It mounts directly to the table and holds the workpiece, using internal gear ratios, either simple or differential kinematics, to rotate the part by incredibly precise fractions of a degree. Why on earth do you need this? Well, if you're cutting the teeth of a gear, for example, you have to divide the circumference of that steel blank into exact, mathematically perfect equal spaces. It's a real game changer.
So, bringing it all together, everything we've covered, from the massive cast iron column to the microscopic rake angle of the tool, all the way to that indexing head, is what allows us to manufacture the modern world. I mean, milling machines produce the perfectly flat sealing surfaces for engine blocks, they cut the complex gears for your car's transmission, they even carve intricate 3D contours for life-saving medical implants and critical aerospace components. They really do it all.
So, here's a question for you. As fully automated CNCs continue to take over the industry, how will mastering these foundational kinematic principles give the next generation of engineers a crucial edge? Well, think about it. The computer might execute the math, but the engineer commands the physics. Truly understanding chip thickness, gearbox logic, and tool geometry, that's what actually pushes the limits of 3D manufacturing. Definitely something to think about the next time you hold a perfectly machined metal part.
If this made the concept click, don't forget to like, share with your classmates, and subscribe so you catch every new problem set.